So this session today is about debugging, and I won't give you, like, this is how you do it. There's no one way to do debugging. You can do it in a variety of ways, and debugging will help you a lot during your professional career, and also during your studies probably. This is a nice quote. I do think that it's actually more valuable than reading 5 minutes of documentation, but sometimes you're just chasing some weird mistake that you made by using a library the wrong way. Obviously, if you write a lot of code yourself and you don't use any libraries at all, then it's probably your mistake. So you will need to debug, and reading documentation, not so much. So, but first, who am I and who are you? And let's start with the who are you. Can you raise your hand if you're programming for the first year? Well, yeah, that's almost everybody. Cool. And raise your hand if you created any bugs before. Okay, that's almost the same set of people. And who of you have debugged before and used debugging tools? Still a lot of people, but not everybody, right? So that's good, because I would just want to explain a few different tools which you can use, and also just show the landscape of what is out there and what I use during in my day-to-day job. As a software engineer, I'm a cloud architect, but also software engineering. Most of the day, I'm just writing software. And that's about me. So I'm Herman Banken, and I am a software engineer at Q42 now for 12 or 5 years, depending on whether you count full-time or part-time. This is our office in Amsterdam. It's actually 5 minutes from here, and we host a nice meetup there, so you could actually visit. And I know before some Codam students have been there before. Me personally, I work in The Hague, and this is a very nice office, also with a slide. But also with a bar this time. And at Q42, which is an agency, so we do work for a lot of different clients. Clients like HEMA, Rijksmuseum, Philips Hue. Mibo is a product that we created, which is actually a spin-off. It's a venture now. And Hack the Planet is a group of people doing stuff to improve the world, like preventing elephants from getting into small cities or villages in Africa, which is really bad if they molest the crop. So I pointed at Philips Hue because that's a project I have been working on for the last few years. I've done some small projects in between, but Philips Hue is the main project of mine, which is a nice project in which we create the software for the bridges to connect to the cloud. So the bridges are all connected to the cloud so that you can say, hey Google, turn on my lights. And this flows via the Philips Hue Cloud. Because Alexa, the voice transcribing happens in the cloud, and then their skill or their software calls us, which needs to happen over the internet and to a public service because it's in their cloud, it's not on their local device. This will change a little bit with Matter and the new smart home standard. But overall, you can control your Philips Hue system out of home, basically. This is a nice picture of the very first bridge, because this has been a long run. We got this engineering sample in 2011 and worked with Philips to launch this product. Somebody was very funny to glue it to some glue sticks, so it looks like a dog. But today, we have 2 clusters running Kubernetes, 39 microservices. Probably 20% of those only are required. No, nobody gets the Twitter joke. So 44 nodes, which used to be a lot more, but we picked bigger nodes now. And they run a lot of different microservices. Those 1,200 pods are the applications themselves with all the replicas. And we do this with a variety of people. Like it ranges from 5 to 12 developers, on average 10. So debugging. If you create such a large system, it happens a lot that you need to do debugging. So it's the process of removing mistakes, that's removing the bug, but it's also understanding the workings of the software. So some of these tools will help you to better understand the software and not necessarily remove a bug, but just find out what's wrong or what's happening. So the obvious one to debug is printf. You probably all used it. It's very simple, sometimes perfect, and it's quite tedious. So let's take a look at some code. I have a sample here, which I did not create myself because I'm not proficient in C. That's other people. This is actually my colleague at Q42, Joppe, who created this code for me, or borrowed because he has written this a long time ago. And he introduced a nice bug for us to figure out. So let's just run this program. Actually, I actually already instrumented it. That's not great. So this program is basically the A2I implementation that you probably wrote already or will write already. Cool. So then this is probably easy to debug because you know the workings of this program. What's happening? Yeah, was not popping up. You see here that I print the digit that is calculated for this number, but it's not correct. Something is going wrong, but what is? So in order to understand what's going wrong, you can open this method and see what it's doing. This method here, yeah, some of you might have spotted the bug already, but don't tell. This is actually first removing any spaces, then checking if it's negative or positive, and then it's parsing individual digits. But where is the bug? Can you tell by looking at it? I see that the result is the thing that's getting returned. So in order to printf debug this, let's just print this result anytime we change it. So like this, and then right over here and over here, and this is not nicely indented. Let's see what's happening if we run this again. That's a lot of output. I should have added a new line. So my debugging is bugged. Oh, this happens a lot, that you change a program and then you need to change the log line afterwards. So I didn't do it correctly still. Save, yep. Great. Yep. So now I have log lines, but this really helped me to understand what's going on. You see a -2 happening there, and then a -20, and I know by heart that the first digit is actually a 1, but it's subtracting 2. So maybe it's subtracting too much. So I have now a hunch that it's somewhere in this line that's going wrong. And I'm subtracting something, but I probably need to just get this into a variable and then and print what this is. And then I can see that this actually needed to be 48. Right? So that's a stupid mistake. But you can actually also do this without printf debugging. So let's remove those. And do something else. So I do make clean debug, which Joppe prepared for me. And instead of now running it manually, I can start. I heard somebody say it in the audience. Use LMDB to connect to this program, basically load this program, and then say run to run the program again. And this is an interactive shell, so I can create breakpoints here. I can, for example, do breakpoint set, and then on the line that I was interested in is now actually 5.3. So I've put a breakpoint now, and I can list them with breakpoints points list. And I can run it again. And then you see that it pauses the execution at this line. So I'm hoping that you can read this, but should I make it a little bit bigger? Oh, that's too big. So it shows a nice arrow where it stopped. And actually, now you can also look at variables. So I can inspect the value of result. I can thread continue, if I'm right. And then do this again, and I'm actually at the next iteration of this this line. But this is quite tedious in this interactive shell, right? So it's good that this LLDB exists because a lot of editors actually integrate with these tools, and they integrate with all of them. So there are a lot of different debuggers, and in IntelliJ and also Visual Studio Code, you can have this nice debug button here, and using that I can debug this at once. So I just put a breakpoint over here, and it stops right there. So now I can see that result is still 0, that is negative is false, and what is actually parsing. So you see that it's reading the 1, and if you actually go to the next line, you see that now result is -2, and then you immediately know that this was wrong, and you fix the bug. So this is great. You can also do watch expressions. You can watch expressions. You can even write some code that changes variables. That's easier with LMDB, I think. I'm not sure if Visual Studio Code exposes this feature, but you can actually set global variables. So you can do, you can watch global variables, and when they are set to a certain value, you can get a trigger, or you could actually change them while the program is running to avoid having to recompile. And if you didn't create the code yourself, that really helps. So you can just tweak, fiddle around with the program. Of course, it needs to be built with debugging enabled, but suppose it is, that really helps you. So those debuggers. There's GDB, LLDB for most of your C programs, but there's also Python debugger. Delve is used for Go. I personally was developing web technology before doing any programming at all. So I used a lot of web browser inspector and pausing there. You can do remote debugging, so the code is running not on your computer, but it's running in the cloud, or it's running on somebody else's computer. And you attach your debugger to that program, and you can actually pause that execution. But if you do that in a production system, then your production system is halted, which isn't really great. So there's another one that is called snapshot debugging, where you do not pause the execution of the program, but you basically fork it and copy the memory, and then let the program continue, but create a snapshot which you can inspect. And you can use nice tools in these debuggers, so breakpoints, logs, and you can inspect values in the memory. So I showed this already, so let's skip over this. It's the same demo. Snapshot debugging, I mentioned this. Actually, I have this application running here. I deployed it to Google Cloud Run because I'm really a Google person in that sense. It's very easy to deploy something like this. And this is actually doing the same A to I conversion that I wrote in C, but this is running JavaScript because it's actually easier to debug. So if I go to this page, it returns the result of A to I-ing this value here in the query string, which has the same bug. So if you look at this, you see that it's consistently bugged. So this is the Google Cloud Debugger, which allows you to load your code. And I rewrote the same program in C into JavaScript. So here you see that I can actually click on this column here and create a snapshot right when this line executes. So it marks it as a break point, and it says waiting for snapshot to hit. So let's rerun this code a few times, and then you see that it actually it captured this snapshot. This UI is a little bit bugged, but if you click on the status line, it jumps to where it actually captured the snapshot. And you can see here on the right the call stack, but also the values of string, the result, if it's negative, and some context, which is also gathered. This is very cool, this tool. You can use this for production debugging. But unfortunately, Google decided to kill this, so it's one of the projects that they killed. But it's open source now, so you can host this yourself by using the link in the slides, which I will share. And you can connect it up to Firebase, and then your application will listen for breakpoints and emit at any time when the snapshots hit. That's nice for small examples. But in a production system like Philips Hue, this is actually an output of Philips Hue logs for one application. You see that there is a 10-minute window selected, and there are, well, thousands of logs. And they all interleave, and it's very hard to have an overview of what is actually the control flow and the logs related to this control flow, because one session is not necessarily grouped. One session could be on the next page, continue on the next page, and that's very hard to see. So what you actually want to do, instead of logging, is using tracing. So let's give a demo of this right away. I created a toy example, which is also going to be linked after in a repository which you can find in the presentation, of a microservice calculator. So this is a very advanced application where you can enter an equation. You can do anything you like except parentheses and power and that kind of stuff. It's just plus, minus, multiples and divisions. And then you can calculate, and it returns a result. You see it was quite slow. That's because I added some latency, artificial latency, and also because it's a microservice. And it's not doing this in JavaScript, but it's actually going to a server, another server, and then going back. So not the most efficient way to do this. But if you have, for example, a real system with a card service and some other service, it makes sense to split stuff up, especially if multiple teams work on different features. So this is just to emulate the situation. So to show it again, how these microservices work. So I created a front end, which you just saw, an equation service, which takes the input that you type and turns it into a normalized format. And then there's a calculator which calculates individual calculations. So it doesn't do the whole thing, but it needs to have the individual ones. And if you trace this application, it looks like this. So tracing is actually adding some extra information to a request and sending for each interaction that the system has information to a central point. So for example, logging service, but this is Google Trace, tracing service, where you store of all these different systems running together, all the traces. And basically they record spans, which are these blue bars, which have a start time and an end time. And typically this would be the execution of one function, for example, or the retrieval of one resource, or making an HTTP request. That would be one span. And then there can be multiple in one trace. They all link to the same trace parent. And in this waterfall graph, you see how they interact. So the first the request is at the top, And there are some calculations being made below. So it's the second span starts a little while after the request, and that's because I actually inserted some artificial latency right there. So here you see a nice red exclamation mark. That actually means that this request failed. And in the right side, you have some details. So you see that the status code of this HTTP request is 500 error. And you can dive into the subspans to see what's going wrong. So it did a solve. In order to solve, it needed to parse the equations. So you see a lot of parse equation calls happening. This is all in the same application. You can see that from the, you see here the service being equations. So this was the front-end application, service front-end. Then solve is still front-end. Equations is service equations. And the calculator sits below in this particular waterfall, but that's in a different service. So you can also collapse these waterfalls, and then it's a little bit more clear. So you see the amount of time it takes, for example, but also the status code it's returning, and this one failed. So if you take a look at what is actually failing, it says status code 2, which is error, and status message division by 0. So that was what was going wrong in this example, and that's why the outermost request failed. All of these different interactions are shown in this plot here on time, so you can find the slowest request and figure out why it's actually slow. You can also filter this, so I filtered it on front end. You can also filter it on status 500 to only find the errors. So these are all failing requests. And they're all, I can spoil this, the same error. But I can also view the successful ones. Yeah, so that's this calculator, and I can also show that it's actually erroring if you divide by 0. So then you get this nice error. So this is tracing. What I really would like now is a profiler for my computer, like what is actually being the thing that's controlling my input and making it slow. So let's go over this one more time. So tracing is nice if you have multiple actors. So you have a microservice setup. And also it shows you the duration instead of only breakpoints and logs and fiddling with individual interactions. It shows the bigger picture in that sense. You can also enable logs. I didn't do that in this demo. If you click this button here, it will inline all the logs for this trace, which is really nice. So you can see that it says it logged parsing 6 times 6. And then it is parsing 6 and so forth. But there's also profiling, and this is especially useful if your program is slow, if you have a bottleneck, because you shouldn't do premature optimization, of course. But if your program is slow, you can find really easily with profiling what is actually slow. So you have this very large graph. The entire width of the screen is sort of an approximation of 100% CPU usage. It's not exactly like that, but if you profile, you make snapshots of the system, like what is it doing right now? And you do that a lot of times during the execution of your program, and aggregate all of these results, and then you have a amount of time spent in certain functions. You have a whole call stack, so you know if a call is being called from the same parent, so you can group them by that, and that's why they are on the vertical axis. all grouped with their the parent call. And and if it's wider, it means that it's running longer. And you can also sometimes see how much time it actually then is. So that's also give a demo of that. There are, by the way, very different representations of this profiler, this profiling views. Typically, such a flame graph would look red to yellow if you use one of the standard tools, but Google, being Google, does it differently. So I created a toy example. I wrote this in Go as well. It's actually a service which does some busy work. So it just does a lot of iterations of a thing which is fairly complex. So doing a regex expression or JSON in Marshall is not trivial, but it's also not very slow. But if you do it a lot of times, then it becomes measurable. And that's what this application was doing when I run it. So you see here in this this graph that on the main function, about 50% of the time was spent with busy work nested and busy work other. And of this busy work nested, about half of the time was spent in marshalling JSON, and the other half of the time was spent formatting the data. And in the regex, you can see exactly what's taking time as well. So compiling the regex again and again and again might not be the wisest thing, but that was what I actually was doing. So I had the regex compile right here, and if I want to optimize this, I can move it out to the global scope like this, and now this whole section will disappear. So that's a nice way to make your program faster. And you don't actually chase things that are not a performance problem. Because if something is happening only 1% of the time, you shouldn't optimize it. And if it's taking like this thing 7% of the time, yeah, it might be advisable to remove that. Oh, one more thing. You can do this for CPU time, but you can also do it for memory allocations and threads. So I selected CPU before, but if you actually click heap, you see what is using a lot of heaps. And this particular example wasn't really created to show you how memory allocation can be debugged, because this is just generic Go stuff, part of the runtime doing stuff. There's not much allocation at all in this program, but you can do this. And you can also look at at threads. In Go, this would be a Go routine. And all of these tools that I showed, they can be used with any programming language. It's just that for each programming language, there's a vendor, somebody creating the tool for it. But this tool, this principle is available for any language. And then you also have specialized debuggers. And this is a self-plug because I created Arcfiddle.net during my thesis. I was working at the time very much with Rx, which is a library created for stream processing. So if you have a stream of events and you want to chain them together, remove certain events, do sub-processes for each of these events, and then bring them back together. All of these interactions you can combine in very complex ways. And at some point, you will have a giant syntax tree of stream processing. And in order to figure out what's actually doing, you could visualize it. So that's Arcfiddle. It shows you some source code, and you can run this source code, and then it will show the how it actually works. So if I have this example here, which is just 3 values, multiplying them by 2, and then for each of those values, I flatmap with another observable, which has a time component. I can subscribe to that, and then you see this output. So this is live updating, but it's actually done already. And you can click through this let's zoom in a little bit. You can click through this example to see where each of the values is coming from. So this value A, which was produced in the end, the bottom is the end. It came from this other observable, and this value A came from that observable, and you can also see what triggered those merges here by looking at the values above. So you can interact with this graph, but this is very specific to Rx. So if you ever find yourself in a situation where you have a very specific problem and you work with bridges, for example, and you want to view their interaction, you could create a debugger for yourself. So basically help yourself by creating tools to find common situations, to solve common situations easier. That's basically my point of this Arcfiddle inclusion here. If it makes sense, just create a debugger. And in the presentation, there are some links to the LLVM, LDB tutorial, but also some links to tracing. You can send those traces to Google, but you can also send, I actually exported these traces using OpenTelemetry, and you can send them to Google, Datadog, Splunk, all kind of different systems. There's a link to flame graphs in C. And I wanted to highlight, it might not be too related, but if you want to take a look at next steps, CRIU is a very nice process where you can actually suspend the program or copy a program, the complete thing, and then have a state which you can just restart anytime. So you could use this for debugging. If you have a process which is running, and you know it's in a certain state which is hard to reproduce, you can make a snapshot, get it out, and run it over and over and over until you know what is actually the problem with that state. But this is just very advanced stuff to look into. Yeah, so that's actually it already. Cool. So long and thanks for all the fish. You know that reference, but actually at Q42, obviously we have that reference as well. You can reach me at Herman, my email address. We do have internships about 6 to 8 per year. Next half year is quite full already, but if you have a very good application, you might get in, but maybe focus on the next half year. And we do have meetups as well. So the Hitchhiker's Guide is one of our meetups, which we often organize in the Amsterdam office, where we talk about what we do. You get some foods, drinks, and nice interactions. So that's it.
Are there any questions for Herman? We actually don't have any questions from the live stream because we had some technical issues, some bug with the products with the live stream today. So yeah, are there any questions from the audience?
This question is maybe 50% funny, but also a serious question. If you're going to write your own debug program, how would you debug that?
Nice. Yeah, I spend a lot of time debugging this tool. Well, first of all, you probably won't write your own debugger if you don't have a library or a very large program. So I was writing this tool specifically for users of this library. So I collected a lot of samples, first of all, from using, I broadcasted something on Twitter and people gave me their examples and I ran them all. I figured out which of those did work. This tool actually produced a lot of output, and at the time I didn't know about tracing and I didn't know about profiling, so I did it a lot by hand, a lot of it. Yeah. But I think you could just use tracing for the same principles.
Yeah. I mean, a lot of this goes above my head, but do you mean, because the way I think of it is maybe you would use code that you already know is correct to debug your debugger?
Yeah, so you can compare, of course. You can look at the sample which works and a sample which doesn't work. Try to make it smaller. A thing I didn't say, but maybe should, is that debugging is very valuable, but if you have written tests, that's also really nice to figure out what's wrong. So if you actually have some code that you wrote yourself and that is small and easily to understand, then you can just test for it, and you probably won't have the bugs in the first place. So that's also what I did for this debugger, write a lot of tests. Yep. Oh.
Sorry. What do you think is most valuable in the production? Not the production, in the development stage, writing tests for your thing, or should writing tests be the first thing you do, or debugging the first thing you do?
Well, I think in order to ship something to production, you first, and so it's also for development, during development, you first create a lot of visibility, I think. But you can also, that's only when you start implementing. So you have written a function or like a handler for an HTTP request, for example, and you start implementing. The first thing you can do is insert some observability, export something to a tracing system. But before that, actually, you can have written your test already. So if you do real test-driven development, you can just write your test already. Maybe you start with testing.
Yeah, I was thinking that maybe with testing, you can actually find the bugs, and then you can start debugging to actually see where they are.
Yeah.
Something like that.
So that's the thing I often do as well. So if you have a test which, it depends a little bit on how complex your system is and which level of testing you're doing. But if you can instrument your program and then run the test against that program, that's a really nice way to debug your own program. Yeah, because you can just rerun the test anytime that you want. Yeah.
And then you can see if your debugging effort actually works.
Yep. Yep. Good one.
Any other questions? Anyone? No?
No.
Okay, then I guess that's it.
Cool.
Thank you very much. Yes.